So we are going to enter into the next chapter. Okay. So before entering into this chapter, what we are going to do further for the next two chapters actually. So I will discuss about that now. What we are going to discuss in detail about, like I will just give a brief idea about that. Okay. Right. So first, what I'm going to discuss is, it's very simple. I'm going to discuss about flow of fluids. When a fluid is flowing and when it flows in a pipes. Okay, so when it's going to flow in a pipe, and what are the different types of behavior. Okay, actually the part of this will be discussed in this chapter, and part of this will be discussed in a different chapter. So in a proper manner, it is a flow. We are going to discuss about flow only. Right, so first, pipes, in the sense, there is no necessary that, first let me give some examples. Okay, before starting into that, let me give some example. If you take flow of pipes, there are enormous number of examples. For example, you take house. Okay, so the pipes, water will be supplied throughout the house, throughout your home, by using a pipe only, right? Water, the supply of water. Or else you take an example of oil and natural gas. Okay, so oils will be supplied throughout the place by using pipes only. So pipes are used for transferring from one place to another place fluids. And take an example of air conditioning system. Okay, so ducts, that is a non-circular section, will be used for transferring air or gas from one point to another point. And another biggest example which I can give is the bloods which is flowing through your veins. Okay, so veins are going to act as a pipe, and like the bloods are flowing through that. Okay, so if you keep on asking about this, there are enormous amount of examples. Heat exchangers, like the cooling oil which is supplied in the engine. Okay, so that is also, like I will be using a pipe only, right? So there are enormous examples. Everywhere there is going to be some type of flow which is going to happen inside a pipe. So pipe means, you might have a confusion, pipe, how I am saying that pipe again and again, because there are two different types of pipes actually. Okay, so I can classify pipes into circular pipes and also non-circular pipes. See, first, circular pipes. Circular pipes means exactly whatever you thought, that is only the cross section of the pipe will be circle. If it is non-circular pipe, okay, so if it is non-circular pipe, the cross section is not going to be circle other than circle. For example, it can be rectangle, it can be triangle or something like that. Especially these non-circular pipes are called as ducts, and the circular pipes are specifically called as just pipes. Okay, so to avoid confusion, I will be using circular pipes and I will be using a rectangular duct or the specific values. Okay, so ducts are nothing but non-circular, pipes are nothing but circular. See, and this circular pipes are majorly used for transferring liquids from one point to another point, or from one place to another point, or one place to another place. The reason for using circular pipes for liquid, because if suppose I am taking a circular pipe, if suppose I am taking a pipe and in which liquid is flowing, okay, in which liquid is flowing, the pressure difference between outside, okay, so this is outside, that is atmosphere, and inside. Okay, pressure difference between these two is very high. Generally in case of liquids, the pressure difference is high. So since the pressure difference is high, there is possibility for this pipe to get distorted, which means it can get bended, right? So to avoid that, I am using circular pipe. Circular pipe can resist that distortion. Okay, so compared to ducts, circular pipes can resist more distortion. Okay. Now, then when I will be using non-circular pipes? That might be the question, right? So non-circular pipes will be majorly used when you are going to transfer gases. The best example which I can give is nothing but your air conditioning ducts. Okay, so you take any apartment or any places such as hospital, malls, or whatever it is, cinema theater, you might have seen the ducts will be in shape of rectangle. Air conditioning duct will be in shape of rectangle. That is, it is not going to be circular. It will be, most of the times it will be non-circular. The reason is a simple thing. One thing why I am not preferring circular section, because in case of gases, the pressure drop will be less between outside and inside. So And another one important thing is this rectangular section is very easy to manufacture compared to circular section. Okay, compared to circular pipes, rectangular pipes are very easy to manufacture, and since there is less pressure drop, there is no need for me to go for pipes. That is, I don't want to go for this circular pipes. Okay, so I can prefer only rectangular ducts, right? So there is a difference between circular pipes and ducts. We will be talking in deep about pipes, okay, like the flow through pipes. And now, why we need to study about this? Just think about it. As I said, I given many examples, right? Like a fluid flowing through a pipe from one place to another place. If the fluid has to transfer from one place to another place, then I need to use some external agency to transfer the fluid. Nothing but a pump or a fan or something like that. I need to use some external agencies like pump or a fan to transfer fluid from one point to another point. But if I want to run a pump, which indirectly means that I need to supply some power, right? I need to supply some power, that is it is going to consume some energy. Now, the major problem with this is frictional losses. When a fluid is flowing through a pipe, there will be viscosity, right? So there will be friction between the particles, there will be friction between the fluid particle and the surface layer, the surface of the pipe. So because of this frictions, there is possibility for more losses also. Okay, that is nothing but the frictional losses. Okay, so we already discussed about that. That is HL, right? So HL. So the total energy is not going to remain constant. Some energy is going to be wasted in frictional losses. So now if I want to supply power, I need to know how much amount of energy is getting wasted. If I get to know how much amount of energy getting wasted, then only I can calculate how much amount of power I need to supply, right? So studying about frictional losses through a pipe or through a duct is very important. Not only frictional losses, there are another types of losses also called as minor losses. Actually, frictional losses are major loss, and there are some other types, they are called as minor losses, such as when a fluid is when a pipe is taking a bend. When a pipe is taking a bend, there is possibility for loss here, or else when a pipe is suddenly getting expanded, or when a pipe is suddenly getting contracted. Okay, when it is getting suddenly contracted, during these times there are formations of eddies, and due to formations of eddies there is possibility for losses, and these losses are called as minor losses. Okay, major losses are frictional loss, minor losses are such as the losses which we discussed, and I will be discussing about this in detail. Okay, about frictional loss also, about HL also, we will discuss about it in detail in this chapter itself. Minor losses we will discuss in next chapter. That is what I am saying. We are going to divide this pipe flow into two different chapters. Okay, so right. So, and what actually we are going to discuss in this chapter is about laminar flow. So we are going to concentrate only on laminar flow, and regarding turbulent flow also we will be splitting it up. Turbulent flow will be discussed separately in a different chapter. So overall we can say that a flow of a pipe with friction will be discussed in three different types of chapter. One chapter laminar flow, another chapter we will be discussing about turbulent flow, that is at the end, and before that we will discuss about minor losses. Okay, so now as I already classified what is the difference between laminar flow and turbulent flow, but I need to talk about it a bit more. Okay, so we will discuss about laminar flow and turbulent flow somewhat in detail. See, we already discussed about the difference between laminar flow and turbulent flow. We know that laminar flow are nothing but the flow which is going to happen layer by layer, right? So it is going to happen in a streamlined fashion, one layer over the another layer, okay, smoothly. But if you consider turbulent, there is going to be lots of mixing. Okay, so it is going to be random. The motion is going to be random. There is going to be lots of mixing. The layers are going to mix. Okay, zigzag fashion. Now we already discussed about this experiment also. The experiment which is conducted by Reynolds. Okay, so he taken a tube from, like, he's going to supply dye. Okay, so you can see this experiment which we already discussed in detail. In detail explanation has been given when I am discussing about laminar flow and turbulent flow. See, now what I am going to do, I am going to take the same experiment only, but I am going to use I am going to do the experiment 1000 times, which means I am going to use different properties. Like I am going to change the fluid, and I am going to change this diameter of the pipe. So these are the things which I am going to change. So first, if I am going to change the fluid, If I am going to change the fluid, which means the fluid properties are going to change, which is nothing but density, viscosity, right? So density and viscosity are the major property which I am going to change. In addition to that, fluid which I am sending, okay, so I am going to send the fluid at different types of velocity. Maybe I will be sending at a, like I will be just changing the velocities. Maybe at some point of time I will be sending at 5 meter per second, then 10 meter per second, then 20 meter per second. So I will be changing velocity of the fluid also. And also I am going to change the diameter of this particular pipe. Okay, so I am going to change diameter of the pipe also. So these are experiments. I am doing thousands of experiment by changing fluid. First I will change the fluid, I will check, I will change the density, I will change the viscosity, then I will check it, I will change the velocity, I will check it, I will change the diameter of the pipe, I will check it. So what actually I am going to do? See, first let me take velocity, because actually I already explained about that, right? So let me consider density, viscosity, diameter, everything is fixed. I am not going to change. I am sending the same fluid, I am fixing this diameter, I am sending the fluid at some particular velocity, a lesser velocity. When the velocity was low, okay, when the velocity was low, the fluid will be flowing and I will be supplying dye, right? So we already discussed about this. When I am supplying dye, the dye is going to flow one layer over the another layer in a very smooth manner. Okay, so this is going to happen at low velocities. Okay, at low velocities, the fluid layers will be flowing one over the another. Okay, as I increase, and this is nothing but, this type of flow is nothing but laminar flow. So laminar flow is observed by keeping all other things constant. Okay, by keeping all other things constant, laminar flow, we are getting laminar flow by at a lower velocity. As I continuously increase the velocity, the flow which is happening smoothly is getting converted. Okay, it is getting, there was a transition phase, it is getting converted, and I could see a random motion of this same dye. Okay, so the dye started to distribute like this. Okay, so that is nothing but turbulent. So we already discussed about that, right? So we already discussed about the same experiment. So at a high velocity I am getting turbulent flow. Now same type of experiment I am going to do by changing, here I changed the velocity, right? So similarly I am going to change the fluid. If I change the fluid, for example I am taking a fluid with a very less density. Okay, so I am taking a less denser fluid, and also I am doing the same experiment with a very high density fluid. So what you will expect if I use lesser density fluid, what will be, whether the flow will be laminar flow or a turbulent flow? Just think about this. If it is lesser density fluid, which means the molecules which is present in the fluid is less. So number of molecules are less, which means that the molecular transfer or the collision, okay, molecular momentum transfer, the momentum transfer between one molecule to another molecule is very less. Since molecular momentum transfer is less, I can say that the mixing of the particles will be less. If the molecular momentum transfers are more, that is, if they are colliding faster, if the momentum transfer is faster, then obviously mixing will be more. If mixing is more, then obviously it corresponds to turbulent flow. Since density is less, molecules are less, so molecular momentum transfer will be less. Since molecular momentum transfer is less, the flow which I am going to get will be laminar flow. Okay, so generally, so these are some general data. So for a lesser density fluids in the same experiment when I am using, so I am getting laminar flow. Similarly, if I increase the density, molecular momentum transfer will be more. If more molecular momentum transfer, then obviously molecules are colliding faster. If they are colliding faster, then which is going to result in turbulent flow, because it's going to mix easily, right? So that is turbulent flow, right? So this is the first experiment which I did by using low velocity, high velocity, then low density and high density. Now I am going to do by taking what I can say. Now I am going to do the same experiment by taking a fluid which is having lesser viscosity. Okay, so if the viscosity is less, and I am going to do with a higher viscosity fluid. Now just think about this. If the viscosity is less, if viscosity is less, then what will happen? If it is a less viscosity, resistance is less. right? So resistance of flow will be less. If resistance of flow is less, then automatically the fluid particle can mix very easily. If one layer is resisting another layer, if resistance is more, then mixing will be less. But since the resistance are less, the fluid particles can easily mix, which clearly states that for a lesser viscosity fluid, the flow which we are going to get in general is turbulent flow. In general, see, I am repeating the word in general because it's not always true, because laminar flow and turbulent flow, we can decide whether the flow is laminar flow or turbulent flow based on all. I need to combine everything. I need to combine everything. What is that? I will say, just wait for a moment. Now similarly, if viscosity is high, then resistance is going to be more. If the resistance is more, then obviously mixing cannot happen easily. If mixing cannot happen easily, then it's going to be a laminar flow in general. In general, for a lesser viscosity fluid, it's going to be laminar flow by keeping all others constant. That is also very important, right? So by keeping velocity, viscosity and diameter, everything constant, and then I can say that I am going to get a laminar flow. Right, so we discussed about velocities, densities and viscosity, and finally diameter. So if I am going to keep a lesser diameter, I am going to reduce this diameter for a very small amount, and I am going to keep a higher, like a larger diameter. Okay, so less diameter and a large diameter. So what you will expect if the diameter is less? See, it's pretty much clear. If the diameter is less, then the boundary is getting influenced, right? So the boundary of the pipe is influencing the flow. It's going to influence the flow. Since the boundary is directly influencing the flow, the possibility for mixing, you can just imagine, just consider a flow of fluid in your blood, the flow of blood in your veins. Okay, was it turbulent? Since your veins was very narrow, since your vein was very narrow, which means like the diameter was very small, am I getting turbulent flow? The blood is getting mixed? Clearly it is not. It is not getting mixed, right? So if I keep a lesser diameter, then I can say that it's not going to mix because of the effect of boundary. The boundaries of like this boundary in the sense I am saying about the boundary of the pipe. Since the boundary of the pipe is very less, there is no possibility, or there is very less possibility for mixing. So I can say that if diameter is less, then I can classify it to be laminar flow. If it is more, then I can classify it to be turbulent flow. Listen, now we are into very important observation. So these are different experiments which is conducted by Reynolds, and he found out and he found that based on varying this density, viscosity and velocity and diameter, he can convert a laminar flow to turbulent flow just by varying this. Okay, just by varying diameter or viscosity or density, he can convert a laminar flow to turbulent flow. Okay, so once he observed this, but if you see properly, it is not dependent only on one factor, because laminar to turbulent conversion depends on diameter and also velocity and also viscosity and also density. And from observing this, he framed a number called as Reynolds number, which is used for distinguishing laminar flow and turbulent flow. In general, we know what is the Reynolds number formula. Here, Reynolds number for a circular pipe is rho v d by mu. Okay, so it involves density, velocity, average velocity and diameter, and also it involves viscosity. Why I am saying average velocity? Because in general, in a pipe flow, velocity is going to be varying. Okay, it's not going to be constant. But when I am going to talk about Reynolds number or any other forms of numbers, I am going to consider average velocity only, because it is very convenient for us to understand. It's very convenient for us to understand the type of flow by treating it to be one dimensional. If I want to treat it to be one dimensional, then I need to consider average velocity only. This also we already discussed when we are discussing about types of flow in fluid kinematics. Okay, so I'm not going to discuss Reynolds number in this video itself. The official definition, the proper definition of Reynolds number, I will be giving in the next video. Here it is, I just want you to understand it in a much better way. Why we are classifying laminar and turbulent flow by using Reynolds number. So by using Reynolds number, why we are classifying? Because based on the experiments which is conducted by Reynolds, density, viscosity, diameter and also velocity is going to decide whether the flow is laminar or turbulent, not a single factor, not only density, not only viscosity, not only diameter, not only velocity, all combinedly is going to decide whether the flow is laminar or turbulent. So he conducted thousands of experiments by keeping others constant. For instance, by keeping all other constant, he varied velocity. By keeping all other constant, he varied viscosity, and then he determined how the flow is getting transferred from laminar to turbulent, and then he framed an equation, and then he framed a number called as Reynolds number, which is going to decide whether the flow is laminar or turbulent. So in the next video, we will see what is meant by Reynolds number, and we will see the significance of Reynolds.